Okay, this video is on functions and function notation. Now, the word function implies a relationship between a dependent variable and an independent variable. We say that the dependent variable depends on the independent variable. So when we say that y is a function of x, what we mean is the value of y depends on the value of x. So in other words, is a function of just means depends on. Now, the actual formal definition of a function is a rule which takes certain values as inputs and assigns to each input value exactly one output value. Now, the rule part of this definition, a function is a rule, there are different ways of expressing the rule. So, and we're going to look at several different of those ways of expressing a rule. The input values, those are the values of the independent variable. And the output values, those are the values of the dependent variable. Now, let's take a look at some function notation. There's two types of function notation that we're going to be using in this class. The first one we call basic function notation, and it looks like this. This is read y equals f of x, or you could say y is a function of x. And anytime you see this type of notation called basic function notation, this value here, the y, is the dependent variable. The value that's here inside the parentheses, where the x is here, this is the independent variable. And this letter right here, f, that's the name of the function. So anytime I see this right here, one of these examples, y equals f of x, this means y, in this case, is a function of x, which, as we just discussed, also means y depends on x. If we have a function that is expressed this way, this means q is a function of t, which also means q depends on t. And if I have a function expressed like this, this just means n is a function of r, or n depends on r. Now, another type of function notation is what we're going to call combined function notation, and it looks like this. And you'll notice that it kind of, if you take the basic function notation, you kind of squash it together, then you kind of get rid of the name of the function, the f, and you just write the whole thing like this. And this you would read as y of x. So you have a table there in your notes for these three, the same three functions that we had before in basic function notation. And again, in basic function notation, we would say, for this one, we would say y is a function of x. And in combined function notation, this would be read y of x. For this one, q is a function of t. That's in basic function notation. In combined function notation, we would read this as q of t. And in basic function notation, again, we have n is a function of r, And in combined function notation, we would say n of r. Now, notice f of x, this symbol here, it does not mean f times x. F of x means the value of the dependent variable for a particular value of the independent variable. Or sometimes we say f of x means the value of the function for a particular value of x. So example 3, here we have an expression that is in combined function notation, and this is read y of 4. And what it means is the value of y when x equals 4. This is read q of 7, and it means the value of q when, and now let me see the actual variable name that we had for q. Let's see, q is a function of t, so this is the value of q when t equals 7. This one is read n of -3, and it means the value of n when, let's see, n was a function of r. So this means the value of n when r equals -3. Now, we talked about how the function is a type of rule, and there are different ways of expressing that rule. One way of expressing the rule of a function is as a formula. If we express this function here, q of n, if we express this as this formula, q of n equals 5n plus 3, then we can say q of 2, well, if we want to know the value of q of 2, that just means we're going to take the value of our independent variable, the value inside these parentheses in our function notation. We're going to replace that value with the number 2. And everywhere that independent variable exists in our formula, we're going to replace that with 2. So q of 2 just means 5 times 2 plus 3, which is 10 plus 3, which is 13. And now there are a couple of other examples there for interpreting q as a formula there in that example. I'm going to leave those for you to do. Functions as graphs. Formula is one way of expressing a rule, a function rule. Graphs are another way of expressing a function rule. For a function, remember that each input value corresponds to exactly one output value. Well, for graphs, the way this rule, this part of the function definition is interpreted is that we can tell that a graph is a function by using this thing called the vertical line test. So if I have a graph here of some sort of equation, also a relation, we would call it, and if I want to know does this graph represent a function or not? Well, I know that if it is a function, then every possible value of x, any value of x that I choose, it must correspond to exactly one value of y. And I can see that for this particular graph, any value of x that I choose is going to correspond to exactly one value of y. In other words, anywhere along my graph, if I draw a vertical line, it's going to touch my graph in only one place. That means I only have one output value for each input value. So yes, this graph is a function. Now, here I have a graph of another type of relation. This looks like the graph maybe of an ellipse. And I can see right away that there are some values of x that I can choose, like say this value right here. for this value of x, I can see that my function, the graph, excuse me, not my function, but my graph, it actually has two values of y, this value right here and this value right here. So right away I know that this relation expressed by this graph cannot be a function because it fails the vertical line test. In other words, in fact, there are a lot of other places where I could draw a vertical line and it's going to hit my graph in more than one place. So here's an example where I've got a graph, and for each input value it corresponds to more than one output value. So I know that no, this graph does not represent a function. Now, in your notes you've got one more example of expressing a function, functions as tables. We're going to take a look at this one tomorrow in class, along with a few other examples of expressing functions.